We hear a lot about AI getting bigger and faster, but there's a fascinating story coming out of the AI world that isn't just about size. A model called DeepSeek Math-V2 just became the first open source model to achieve a performance level equivalent to a gold medal at the International Mathematical Olympiad. And what's really interesting isn't just that it can solve these incredibly hard problems, but how it's doing it. It seems we're entering a new era of AI reasoning.
That's exactly right. This isn't just another point on a benchmark chart. It's a philosophical shift. For years, AI training was all about rewarding the correct answer, no matter how the model got there. This led to a kind of clever guessing. DeepSeek Math-V2 changes the game. It insists on rigorous, step-by-step reasoning. If any step in the proof is invalid, the model gets no reward. It has to show its work, and the work has to be flawless.
So it's like the difference between a student who just writes down x equals 5 and a student who shows every single algebraic step to prove that x equals 5.
Precisely. And it gets even more layered. They've implemented a meta-verification strategy. Imagine an AI student solves a problem and an AI teacher grades it. But what if the teacher is biased or makes a mistake? DeepSeek adds a principal AI that checks the teacher's grading. This nested review process boosted the reliability of their evaluations from 85% to a staggering 96%. It's a system of checks and balances for AI.
A principal AI? That's a wild concept. So it's not just solving problems, it's also reflecting on its own process?
Exactly. There's a self-reflection mechanism built in. During problem solving, the model can actually pause, evaluate its own logic, and revise its steps if it thinks it's going down the wrong path. It's mimicking a human-like reflective reasoning process, not just spitting out an answer. It really drives home this idea that the path to more advanced AI isn't about raw speed, but about this kind of deep, reflective thinking.
And this focus on more sophisticated operations isn't just happening in pure reasoning, right? I saw something similar with Claude Opus 4.5 and its approach to AI agents.
Right. While DeepSeek is rethinking the how of problem solving, Claude 4.5 is rethinking the how of getting things done in the real world. Its big innovations aren't just about raw performance, but about making AI agents smarter at using tools. It has something called a tool search tool, a tool for finding other tools, and more importantly, programmatic tool calling, or PTC.
Okay, programmatic tool calling sounds pretty technical. What does that actually look like in practice?
Think of it this way. The old way, like the React framework, was like an agent trying to complete a task by taking one small step at a time, checking its work, and then taking the next small step. It could take 100 or more of these little iterations. It's slow and clunky. Programmatic tool calling is totally different. The AI agent essentially writes a single, coherent script upfront that orchestrates all the tools it needs in one go. It's the difference between fumbling around in the dark one step at a time and just writing a program to turn on the lights and grab what you need. It changes these complex 100-step loops into efficient, single-run workflows.
So we have models learning to reason like mathematicians and agents learning to plan like programmers. What are the broader implications of this? Does this reflective reasoning and enhanced agency bring us closer to a more general or even super intelligent AI? Or are we just seeing more sophisticated, specialized tools?
That's the billion-dollar question. On one hand, these are absolutely specialized tools. DeepSeek is a math prodigy, not a general conversationalist. But the times principles, times behind them are what's generalizable. Teaching an AI to value logical consistency, to self-correct, to plan efficiently, these are the building blocks of higher intelligence. Regardless of the domain, it's less about creating a single superintelligence and more about developing a whole new class of AI that is more reliable, verifiable, and autonomous.
But let's play devil's advocate for a moment. While meta-verification and self-reflection sound incredibly advanced, are we sure these aren't just more elaborate forms of pattern matching or algorithmic checks? How can we truly differentiate this from genuine reasoning as humans understand it? And what are the potential pitfalls if we over-attribute human-like intelligence to these mechanisms?
That's a fair and crucial point. We have to be careful with our language. It's not reasoning in the human conscious sense. It's a very sophisticated simulation of it. The principal AI isn't pondering the nature of truth. It's running a validation algorithm on the output of another algorithm. The danger is exactly what you said, anthropomorphizing it. If we believe it truly understands when it's just following a very complex rulebook, we might trust it in situations where its logic, which is alien to ours, could fail in unexpected ways. The goal isn't to build a human mind, but to build a tool whose reasoning process is transparent and verifiable to us. That's the real breakthrough here.
It's clear that the pursuit of smarter, more autonomous AI is driving incredible innovation in reasoning and agency. However, as we make these models more capable in the lab, the real-world challenges of scaling and deploying them effectively become even more pronounced. This brings us to our next point. So, moving from these exciting breakthroughs to the reality of deploying these models at scale, we often see a different picture. Google's Gemini 3 Pro is a prime example. While internally it showed immense promise, its public release appears heavily degraded. Users are reporting things like instruction drift, where the model just ignores what you ask it to do, speaker confusion in conversations, and a noticeable decay in performance over longer chats.
Yeah. And the leading theory is that the culprit is quantization and compression. And this is a classic recurring theme in AI deployment. The lab magic doesn't always translate perfectly to the real world. Gemini's issues really highlight what some call the scaling wall.
Can you break that down? What are quantization and compression, and why do they cause these problems?
Absolutely. Think of a massive, powerful AI model, like a professional photograph, in its raw, uncompressed format. It's huge, full of detail, but it would take forever to email to someone. To make it practical to send and view, you compress it into a JPEG. It's much smaller, but you lose some of the fine detail. Quantization and compression do something similar to AI models. They shrink the model to make it faster and cheaper to run for millions of users. But in the process, you can lose some of its nuance and precision. It might get a little dumber or less reliable.
That makes sense. And it's not just these giant models that face this reality check. I saw that even in seemingly simpler applications, like ByteDance's new AI-powered keyboard Dubao, there are similar trade-offs.
Right? That's a perfect example of where the rubber meets the road. The Dubao input method uses an offline local LLM to improve voice recognition, which is great for privacy and speed, but users are hitting gritty, practical problems. It's bad at categorizing common phrases, it struggles with certain types of punctuation, and there's a noticeable input lag. It shows that even with a powerful AI engine underneath, the user experience can be tripped up by these small, frustrating details. The promise of AI often clashes with the messy reality of daily use.
If we put ourselves in the shoes of an AI product manager, seeing these kinds of degradation issues or user experience complaints, what are the primary trade-offs they're forced to make? Is it always a choice between performance and accessibility, or are there deeper architectural issues at play?
It's a constant balancing act. The biggest trade-off is cost versus quality. Running the full, uncompressed, raw photo version of Gemini for every single user would be astronomically expensive. So you have to compress it. The question is, how much quality can you sacrifice before the user starts noticing and the product feels broken? It forces product managers to decide what's good enough. Sometimes this can expose deeper architectural issues where a model was simply never designed with efficient scaling in mind from the start.
The suspicion that quantization is degrading Gemini's performance raises an interesting point. Are we, as an industry, sometimes prioritizing brute force scaling and rapid deployment over the nuanced preservation of a model's core capabilities? What are the long-term risks of releasing degraded but accessible AI, both for user trust and for the technology's reputation?
I think that's a very real danger. There's an immense pressure to be first to market and to operate at a massive scale. The risk is that we train users to have low expectations. If their primary experience with powerful AI is one that's buggy, drifts from instructions, or just feels a bit dumb, they'll lose trust in the technology's potential. It can also lead to a race to the bottom where companies cut corners on model fidelity to save costs, and the whole field's reputation suffers. It's a short-term gain for a potential long-term loss of user confidence.
The challenges of scaling and real-world deployment are clearly significant, forcing developers to make tough choices. But what if we could fundamentally change how these models are built or deployed to mitigate some of these issues? This leads us to the crucial, often unseen innovations happening beneath the surface in model architecture and efficiency. While we often focus on the massive models, some of the most impactful innovations happen at a more fundamental level. For instance, a model called Qwen developed something called Gated Attention, which just won a Best Paper award at NeurIPS, a top AI conference. It's apparently a simple modification that solves multiple pain points in the underlying transformer architecture.
Yes! And this is why that paper won. It wasn't about a flashy new model from a big-name company. It was recognition that an elegant, simple architectural change can have a massive impact. What's more, they validated it at industrial scale on huge models trained on trillions of tokens of data. It proved that the fix was robust and not just a fluke in a small lab experiment. These are the unsung heroes of AI development, the foundational tweaks that make everything else possible.
It's not just about building a bigger engine, but making the engine itself run more smoothly. I also saw something about Microsoft developing a technique called black box on-policy distillation, or GAD. It sounds like a way to make smaller models smarter.
GAD is a potential game changer for deployment and accessibility. The core idea is distillation, taking a huge, powerful teacher model and distilling its knowledge into a smaller, more efficient student model. The problem was that you usually needed access to the teacher's internal workings, its weights and logits, but many of the most powerful models, like GPT-4, are black boxes. You can only give them text and get text back.
Okay, so how does GAD get around that?
It uses a clever adversarial process. Basically, the small student model tries to generate an output that's indistinguishable from the teacher model's output. Another AI, a discriminator, tries to tell them apart. By playing this game over and over, the student model learns to mimic the teacher's style and quality with incredible fidelity, all without ever seeing its secret recipe. It allows us to create smaller, cheaper, high-performing models from these massive proprietary ones.
That's a fantastic analogy. It's like an apprentice learning to cook just by tasting the master chef's dishes. So, from the perspective of a small startup or an independent researcher, how do innovations like GAD change the landscape? Does it level the playing field?
It absolutely does. It democratizes high performance. A startup can't afford to train a GPT-4 level model from scratch. But with a technique like GAD, they can potentially use the public API of a large model to train a much smaller, specialized model for their own application that is nearly as capable for that specific task. It lowers the barrier to entry for building high-quality AI products.
And this theme of elegant solutions and rethinking fundamentals seems to apply to generative AI as well. I saw that He Kaiming, a legendary researcher in computer vision, has a new paper that challenges the way diffusion models work.
Yes, and it's a classic He-Kaiming move. Going back to basics, for years, diffusion models, the tech behind things like Midjourney and Stable Diffusion, have worked by learning to predict the noise that was added to an image and then removing it to generate a clean picture. His team's new paper basically asks, why predict the noise? Why not just predict the final image directly? It's a much more direct and minimalist approach.
And how does it perform? Is it better?
In terms of raw benchmark scores, it's slightly behind the absolute state-of-the-art models. And this is a big but, it often yields better times, usability asterisk. It simplifies the entire process. It's a reminder that the best technical solution isn't always the one with the highest score, but sometimes the one that is simpler, more robust, and more intuitive to use. It's about making AI not just powerful, but also practical and sustainable.
It's clear that these under-the-hood innovations are critical for the long-term health and progress of AI. We've explored how AI is getting smarter in its reasoning, the tough challenges of bringing it into the real world, and now the foundational tech that makes it all possible.
Exactly. The headline-grabbing models are like the tip of the iceberg. The real lasting progress is happening down here in the architecture, in the efficiency, and in the fundamental principles. The focus is shifting from just raw power to verifiable reasoning, self